Hi, my name is Hugh, and this video we're going to familiarize you with the multiple gas number 5 GC configuration. It's built on the 8610 GC sized chassis, but inside the GC there's an arrangement of parts, injectors, detectors, valves that makes it into this particular configuration, which is a wonderful way of measuring hydrogen, oxygen, nitrogen, methane, CO, CO2, ethane, ethylene, propane, butane, pentane, and all the way up to toluene, depending on how long you want to allow for the analysis. So it's a very useful analysis. We've sold quite a few of these, and this video is just going to really kind of orient you to the parts of the multiple gas number 5. We're not really going to explain in gory detail how it all works, because there's a wonderful document that's available on our website, 30 pages long, that explains everything that I'm going to say, but in greater detail. So this is just to kind of get you oriented so that you can relate better to the document and understand how the GC works. So the heart of the GC is the arrangement of the valves and the columns. The valves, there's 2 of them. There can be a third one depending, but there's 2 of them in the standard model, and this valve injects the sample onto 2 of the columns in this column oven. This valve injects onto the 3rd column in the column oven. So the valves are controlled by something called relays. So this one is controlled by relay G, this one's controlled by relay F, and there's a little map on the top of the cover of this valve oven that shows the way that the gases flow through these valves on their way to the columns, and then what happens. And it's a little bit complex because the flows change when the valves are actuated, and that's part of the cleverness of this design, is that if you follow our little recipe, there's no orphan molecules. All the molecules that you inject, including water, are accounted for and either measured by the detectors or gotten rid of by the pre-column backflush or by the other backflush. You see, it gets a little technical, so but we don't care about that right now. Just want to show you how it all kind of works together. So to load the sample through the valves, you connect some kind of a gas supply here, and it goes through these tubes in the valve, and then it comes out here. So watch, I'm just going to take a syringe of air, and then I'm going to connect it to the sample in, and then I have a little beaker of water here. And so when I push on the syringe, you can see the bubbles, right? If I stop pushing on the syringe, the bubbles stop. If I blow here, then the bubbles come out, because you're not fighting against anything. When you blow the sample through here, you're really just blowing it through empty tubing. And it doesn't matter whether you blow a little or a lot. All that really counts is what's left in the tubing when you stop pushing the gas through. So it doesn't take any force really at all to push the sample through. So you can load the sample with a syringe, or you can connect a calibration gas bottle. See here, I'm going to connect this here, and then these are 1/8 inch swage lock fittings. So all you really need to do is have some kind of tubing that you can adapt to 1/8 inch swage lock. So this is your calibration cylinder, or it could be your reactor that's producing a constant flow of gas that you simply connect through here and let it exhaust into the water. So if I open this and let a little bit of gas through, you can see there's a lot of bubbles coming all the way through. So I would stop the flow of gas and then start the analysis, and then whatever gas was left in the tubing gets pushed by the carrier gas into the columns. So there's 3 columns in this GC. There's an 18 inch Hayes-Sep D pre-column, right? And that's intended to catch the peaks that we don't want to get onto the analytical column, which is a molecular sieve column, a 3-foot mole sieve. So here's this little 18-inch piece, and then here's the 3-foot or 6-foot mole sieve column, and that separates hydrogen, oxygen, nitrogen, methane, and CO, and that's it. It doesn't, if you let CO2 get onto that column, then it gets stuck. If you let water get onto that column, it gets stuck. So we have to keep the water and the CO2 from getting onto this mole sieve column, and that's the job of this 18-inch HACEP pre-column. It catches the heavier molecules and then back flushes them out this vent tubing here on the front. The other column is called a HACEP D column, and this column separates air. It doesn't separate oxygen from nitrogen, but it separates air from methane, and then CO2, and then ethane, propane, butane, pentane, and higher. And that column is this 6-foot HACEP D column. So one of the things that is important is the amount of gas that you have to push through the loops. There is some minimum amount that you have to have in order to flush the old gas out and the new gas in. And that amount, the minimum amount that you need is 10 milliliters, right? So you would have to push at least 10 milliliters of gas through the loops in order to make sure you'd flushed out the old gas. And now what was sitting in those loops is the new gas. So sometimes in some experiments you just don't have that much gas to work with. So it's also possible to make a smaller volume gas injection directly into these ports here that are called on-column injection ports, because those go right into the columns. And because this has got a little rubber plug, the gas is going through here, you can squirt it in, and it goes through almost like using the valves, but it allows you to work with a much smaller volume. The document on the website explains exactly how that will work, and it's easy with one of the columns, and it's a little more complicated to do it with the other set of columns because the valve has to be in the right position before you squirt that in. But that's a detail we don't need to really worry about here in this video. So the last thing is that these are the detectors, right? This is the thermal conductivity detector. This is the FID detector with a methanizer. The methanizer converts the CO and CO2, if there is any in the sample, into methane, so it can be measured much more sensitively with the FID detector. The FID detector is about 100 or 200 times more sensitive than the TCD, but it only detects hydrocarbons. It only detects molecules that have hydrogen-carbon bonds. So by converting the CO and CO2 to methane in the methanizer, which is a nickel tube that's heated, and the CO and the CO2 react to make methane in that heated catalyst tube and then get detected. So that's what this is, the TCD, and this is the FID. This is the control that turns the TCD current on or off. There's two positions. There's a low position and there's a high position, and the middle is off. Depending on what carrier gas you use, you can maybe use the high current setting, but if you're using argon or nitrogen carrier, then only use the low setting, because the high setting can be too high with carrier gases that have low thermal conductivities. The filaments just get too hot. And then the FID detector has a gain switch also. It has high in the middle and then medium and low. Normally you'd run on medium, but sometimes high or low makes sense depending on how much sample you have. The idea is that the flows of gas, the carrier gas, go through the TCD detector, and then they exit the TCD detector through a little tube that goes into the FID. So the two detectors are measuring the same molecules. They go through the TCD, they don't get altered, they just get heated up a little more maybe, and then they come back out in the tube, and then they go to the methanizer where they're burned in an actual flame consisting of hydrogen and air. Most of the GCs have a built-in air compressor that supplies air to support the flame. That's coming in through this little tube right there. And then there's a supply of hydrogen that goes to make the flame. And when the hydrogen and air combine, they make water, and you can actually see a plume of water vapor coming out the end of the detector. That's your evidence that the flame is lit. The flame is lit by this thing here called an igniter, which is a red hot ceramic bar that really never burns out, and it will stay red hot forever and light the flame if there's hydrogen and air present. If there's no hydrogen, it won't light. No air, it won't light. You can turn off the air here on the front panel with the air compressor on and off. So that's the basic familiarization with the hardware. Hope it's helpful. and give us a call if there's any problems. Thank you.